The first talk will be given by Mondal, exploring Increasing-Chord Path and trees.
So, hello everyone, thanks for coming to my talk. So, I will be talking about increasing-chord paths and trees, and this is a joint work with Yegane Bahu, Stephen Durocher, Shahar Meherpur and myself. So, I see Stephen is there, so if something is not clear, you can also ask him the questions. And Yegane is also here, but probably she preferred the other talk because she knows everything here. So, okay. Let me see. So, let us start with the definition of increasing-chord paths, right. So, I want to show you an example. So, I want to show you an example of path and then I will define what do I mean by increasing-chord. So, I choose any 4 points A, B, C, D in this order on the path. So, here are my 4 points A, B, C, D on this path, and if you see the distance between B, C is smaller than the distance between A, D. By distance I mean Euclidean distance. So, if for every 4 points A, B, C, D in this order on this path has this property that B, C has a smaller length than A, D, then I call this an increasing-chord path. So, here is another example of such a path. So, here you see I have 4 points A, B, C, D in this order, and again B, C, the distance between B, C is smaller than A, D, and that is true for every 4 points A, B, C, D in this order on the path. So, these types of paths I call increasing-chord. Now, you might wonder that what are some examples where the path is not increasing-chord. So, here are 2 examples. So, I can choose 4 points on this path as shown here A, B, C, D in this order on the path, but the property does not hold, like the distance between B, C is greater than the Euclidean distance between A, D. And here is another example. So, these paths, by the way, here is the author Yagana. So, here these are 2 other examples where the paths are not increasing-chord. So, first time I saw the definition of increasing-chord paths, it was not very easy for me to comprehend, but this path has such nice properties that I am going to show you right now that it will become intuitive. So, there is an equivalent definition. So, you are given a path, you want to say whether it is increasing-chord path or not, and it is defined like take any point on the path and draw a perpendicular to the tangent. If it does not intersect, then it is the same property. So, you take arbitrarily any point and you draw the perpendicular to the tangent. If it does not intersect the path anywhere except at P, then this is an increasing-chord path, but the point P must be arbitrary. It holds for every point on the path. Okay. So, if I want to test whether the paths that I showed earlier that they are not increasing-chord using this criteria, then I can find a point P and draw the tangent, and you can see that that intersects some other point like here and also here. So, these paths are not increasing-chord. So far so good. Okay. So, now you can ask why I am interested in this type of paths, right. So, think of a geometric graph where every pair of vertices are connected by increasing-chord paths and call them increasing-chord graphs. Okay. It turns out that this type of increasing-chord graphs have low dilation. So, if I take any pair of vertices in my graph and I ask what is the ratio between the shortest path length divided by Euclidean distance between the vertices, that ratio will be a very small constant, like at most 2.094, and that is a very nice property that is used, or that motivates us to find such paths in a graph to route the messages. If you think of a network, want to route a message from one point to the other, this type of properties are very likely to explore. And it happened that in many research, it has been explored. The questions we ask for in general geometric graphs, we can ask for also increasing chord graphs. So, for example, if you are given a set of points, you can ask, can you find a spanning geometric graph with a small number of edges which is increasing chord? We ask those for monotone properties, spanning properties, and similarly the increasing chord properties, and there are lots of work. There is another direction where you are given a geometric graph, and the question is test whether this graph is increasing chord. Well, there is another major research direction. So, you are given a graph, combinatorial description of the graph, and you want to find a drawing that is an increasing chord drawing. So, among all this related research, there are two special, very interesting open questions that I want to look into this presentation. The first one was asked by Alamdari et al. In 2013, that given a geometric graph and two vertices S and T, the question is, can you in polynomial time find a path or decide there is an increasing chord path between the given vertices? So, this is one of the most natural questions to ask. Given a geometric graph and two vertices, are they connected by an increasing chord path? Okay. So, the next question is asked by Mastakas and Symvonis in very recently 2017, and they asked that again given a geometric graph and a vertex R, can you find a rooted spanning tree? So, a spanning tree rooted at R such that any root to leaf path is increasing chord. For example, here is a spanning tree for this graph where the root is R and any root to leaf path is an increasing chord path. Well, so we show that tree problem is NP complete. So, if you want to decide whether there is a rooted spanning tree with increasing chord property, that is NP complete, but we could not show the path problem to be NP complete. I will tell you later why we couldn't and what are the ideas we had, but some of the ideas for trees would apply also to paths, and we will see that later. But first I want to show you the brief description of the NP hardness proof. So, the reduction is from 3 set. So, you have lots of variables and clauses have at most 3 variables. Okay. So, I want to describe that hardness proof very briefly with a high level description of some graph that for this presentation we can call cascade graph. So, what do I mean by that? I have one edge per variable. So, x1 has this bold edge right over there, x1 bar has this edge, and so on and so forth. And again this graph has 2 special vertices. The bottommost is the root R and the topmost I call T, and there are some other edges. Now, what is the property of the graph I want to satisfy is any y monotone path from the bottom vertex to the top vertex must pass through xi or xi bar. For example, here are 3 monotone paths from R to T. So, the first one chooses to go through x1, x2 bar and x3 bar. The second one chooses x1, x2, x3 and so on. So, later in the reduction I will replace this y monotonicity with increasing chord property. Okay? And the description will not be such simple, it will be a bit complex, but essentially what we are going to show is given a 3 set instance, we want to construct equivalent geometric graph and the vertex the root R such that if there is a rooted spanning tree with the increasing chord property, there is a satisfying assignment of the tree set, and vice versa. Well, so how do we exactly construct that? So for every variable I had an edge and I put them on top of each other, and with some nice property and some nice rotation such that they form a nice projection, perpendicular projection. What do I mean by that? So these are very tiny little edges on top of each other, and if you draw perpendicular to the edge, then they form these nice slabs, and these slabs are very thin. If we extend them, it will form a nice regular arrangement. And what's the special property of the arrangement is, if you look at the upper envelope of the arrangement of the projections, then each segment from this side to the side far from me will be ordered like this. So the first segment will correspond to the first variable x1, the next is x1 bar, the next to x2 bar, and so on. Well, so we have this initial setup for our variable gadget. Okay, now what I want to do is I want to build a cascade graph here. So I have this special root at the bottom and the vertex at the top, and the idea is, if you have a spanning tree, then there must be a path from R to T, and that will choose some of these variables, and based on which variables have been chosen, I will set the truth value to the variables. Okay, so this is the setup for variables. Now what happens to my class gadgets? To construct the class gadgets, these are not that difficult. I create some class points. So the class points are these points right over here. You can see a very particular class, that is x3 or x2 bar or x1. Now what do I do with that is, for every variable I construct a point inside this arrangement. So the first one is from this side is x1, so I put a point right below the segment of x1 and connect that point to that class point and to T. And there are 3 of them, so I have 3 points x1, x2 bar, x3, and I connect each of them with the class point and to T. So that's very simple, and that's it for this particular class. And there are other class points for other clauses, so I do the same thing for them, and that's my construction. I have a few edges coming from here and goes over there. I didn't describe them, those are not necessary right now. But with this setting we can say something, that if there is an increasing chord spanning tree, then we can satisfy all the clauses. How we can say that? Well, so if it is a spanning tree, there is a path from root to this vertex, and we know by cascade graph that we choose some of these variables by going through some of the edges here. Well, now if I choose say x1, then I choose the edge corresponding to x1, and if you remember, if we look at the projection of the edge, perpendicular projection, then that would intersect some of these edges over here. So for example, if I choose x1, this green one will be selected, and I cannot go past x1, because in that case that will not be an increasing chord path. So what we need to argue here, if we can reach to the class point, if we can do that, if we can reach to the class point, then we can find an intermediate point through which I am going to the class point, and that one I haven't selected, because if I selected that one, that will intersect with the corresponding point, and that will not be an increasing chord root to leaf path. So this way we can say that if there is an increasing chord rooted spanning tree, then we have an increasing chord, we have all the satisfying assignments. And this is the big picture, where I also have some parts that I don't want to describe right now. And if you want to see the other side, if you have a satisfying truth assignment, then I first choose this root to T path, and that's my truth values. and then I go from T to the clause points and satisfy all the clauses, and there are some other paths that I can go from R to those paths to create the spanning tree, and that ends the NP hardness reduction for trees. Now, I want to go very briefly and quickly how this idea can be transformed to have some reduction. Hopefully, someone will be able to prove to show the hardness. Now, there are levels of arrangements. So, the first arrangement is exactly the one I showed you for the trees, and the projection of those create the next level arrangement and so on, and each of these level have these variables correspond to that. So, if you cross one level of arrangement, you choose some of the variables, and the messy part of the construction is if you choose x1, x2 and x3 here, that will correspond to the same choice for all the levels. And if you can go from the bottommost level to the topmost, that is the ST path, you satisfy all the clauses. So, that is the idea, but we could not prove the construction to be bounded in polynomial or even exponential number of bits. So, the reduction is not giving you any NP hardness reduction. So, the open question could be show that it is hard or solve it in polynomial time. The other natural question is we can do all sort of hardness reduction when we have crossings. What happens when you have planarity restriction? The second question is how fast can you solve it for special classes of graphs like Delaunay triangulation, and can you do something like FPT? Maybe the most natural parameter you can look for is the number of edge slopes if it is bounded. So, I think I will leave it to that, and thank you for your kind attention. Okay, so it's a very it's a very nice question, and there is a very recent paper. I don't know whether you are one of the authors. I don't know, but okay, if not, then there is some work that given a polygon they test which points have increasing chord property with respect to the boundaries on the polygon and how to find those. But I have to look into that in details. So far, I don't remember. Yeah, but there are works on polygons and very recent. Yes.
Is it known that every Delaunay triangulation, every pair is connected by an increasing chord path?
Well, that's the thing. Not every Delaunay triangulation is increasing chord. That's why I want to say how fast can we maybe test it. It could be NP hard, but it is very unlikely. But there is no algorithm, so yeah, it is very open even for Delaunay triangulation.